Section 1.3, we're going to go over different types of data. In this course, there's two main types of data that we're going to be looking at. Did we go over those at all, quantitative and qualitative data? No. All right, but we did go over a population parameter and a sample statistic. In this section, the key concept is the subject of statistics is largely about using sample data to make inferences about an entire population. The key words here being sample and population. So we're going to be looking at sample statistics and population parameters. Remember that from the previous lecture. So a parameter is a numerical measurement that we use to describe some characteristic about a population. Do you remember what some of the parameters were that we looked at last time? What does this one represent? Average, and what do we call this? Mu. It has a name, it's called the Greek letter mu. It means average. What did we call this one? It's a proportion. And then another one, what symbol is this? What do we call this? Laying down what? Laying down P. It's a lowercase sigma, and it's for the standard deviation. Okay? Some sample statistics we looked at last time would be what? What's the average for a sample statistic? X with a bar over it. What about the sample statistic for the proportion? P with a hat on it. And then the sample statistic for the standard deviation is a lowercase s. Do you kind of feel comfortable with the concept of a population parameter and a sample statistic? The sample, remember, is a subset of the population. Alliteration helps us keep this straight. Population parameter, P and P, sample statistic, S and S. On your test, I'll have questions where I give you a scenario such as, out of a survey of MCC students, 15% said that they like commuting to campus. Would that 15% be a statistic or a parameter? A statistic, because it's based on a sample. An example of a parameter would be something like, for this class, the average on the test was 83. The test average was 83 in this class. I'm interested, my population is just this class, and I've got the class average, so that would be a population parameter. Now, if I took a random sample of, say, 3 or 4 students and just looked at their tests and averaged it together, then that would be a sample, based on a small sample from the students in this class. Now, if I was talking about how all of my statistics classes do on the first test, and I just took your class's average to say something about all of my statistics classes, then that average would be a sample statistic. So it depends on the context of what you're talking about. And remember, in the previous section, we said one of the things we have to do is understand the context of the data. And so that's where you have to understand, are we talking about an entire population or just a sample? The two types of data that we will be working with are categorical data. Sometimes we refer to this as qualitative data. And it consists of either names or labels that represent categories. We can have numbers in here represent a category, and we'll see some examples of that in just a minute. Quantitative data is the other type of data. These are the two types of statistical research that you have available as well, qualitative and quantitative. Qualitative focuses on characteristics or qualities of things. Quantitative looks at a number, a quantity of things. And quantitative data, it consists of numerical data that represents counts or measures. Okay, so those are the two types of data. Now, quantitative data can be further broken down into either discrete data or continuous data. And I will ask you on your test and in your homework to identify whether or not the data represent discrete or continuous data. But if we talk about discrete and continuous, know that we're talking about quantitative data. Discrete data result when the number of possible values is either a finite number or a countable number. It could be infinite, theoretically, as long as you can enumerate or count. For example, the number of stars in the sky would be an example of discrete data, because we have 1 star, 2 star, 3 stars. I can count them. Even though there's way too many for me to count, they're theoretically countable. Does that make sense? All right, continuous data result from an infinitely many possible values that correspond to some continuous scale. The difference here being continuous scale. We can have an infinite number of discrete data, but if they're not measured on a continuum, then they're not continuous. By a continuum, I mean we can measure to whatever level of precision that you like. For example, if we're talking about the height of a tree, it could be 17.34579 feet tall. But that 0.3479, I can measure to whatever level of precision that you want there. But if I'm talking about the number of leaves on the tree, I can't have 17.3445 whatever. It's either 1, 2, 3, 4, or 5. Does that make sense? This concept I'm going to kind of stay on for just a minute because it does tend to cause problems and confusion amongst students. So let me give you one more example. If I'm talking about the length of my hair, would that be discrete or continuous? Continuous. The length of my hair is continuous. I can measure to what, and it's growing. So, but what about the number of hairs on my head? That would be discrete. Even though I don't want to sit and count every hair on my head, I theoretically could. What about the amount of milk that a cow would give? That's continuous. The number of eggs a hen would lay. Discrete. Yeah, chickens lay eggs forever and ever and ever until they don't. And that's why our mind thinks continuous. But we can count 1 egg, 2 egg, 3 egg. If you have a half an egg and you come in the house after gathering eggs with a half an egg, your dad's going to be mad. Eggs are discrete. Milk is continuous. What about shoe sizes? The size of your shoes. Discrete. The shoe size is discrete. It's not as easy as it sounds, is it? Shoe size is discrete because you could wear a 6, 6.5, 7, 7.5. Even though it's a half, we don't measure them at the 7.325, right? It's either a 7 or a 7.5, an 8, an 8.5. So those are discrete. We can enumerate them. But the length of your foot now, there's a whole bunch of different lengths of feet that will fit in a size 8 shoe. Granted, they're within a certain tolerance, but there's a whole bunch of different lengths. Can you think of an example of something that would be measured discretely? You come up with it now. If I ask you to write down an example of something that's measured discretely, what would it be? How many gallons? Is that discrete? That would be continuous. Good example, but it's continuous data because the amount of water in the lake is continuous. We don't have just 1 water or 2 waters or 3 waters. I know you said gallons, but we could have a fraction of a gallon at any fraction. Does that make sense? So the amount of water in the lake would be continuous. We're still trying for discrete. How many trees are in the forest? That's discrete. How many what? How many pills are in a bottle? That's discrete. Levels of measurement now. If we have numerical data, there are certain levels of measurement, whether or not the data are discrete or continuous. The first or the lowest level of measurement would be the nominal level of measurement. This is data that's characterized by it consisting of names, labels, or categories only. It doesn't make sense to arrange the data in any ordering scheme such as low to high. So even if we have numbers representing things, those numbers would be categories. For example, have y'all seen the commercial? I don't know if they do it anymore, but there used to be a commercial where they do a blind taste test, and they have different sodas. Like Coke will be behind number 1, Pepsi behind number 2, Dr. Pepper behind number 3. Those numbers are arbitrarily assigned to the soda. And then people drink the different sodas and pick what's their favorite. Those numbers just represent categories. They're taking the place of the name of a soda. So people don't know in advance what they're drinking, and hopefully then they pick what really is their favorite and not being loyal to a brand. That's an example of nominal level of measurement of data. If you can assign survey responses of yes, no, or undecided, you could even assign numbers to these. Yes could be a 1, no could be a 2, and undecided could be a 0. You assign numbers, but those numbers are arbitrary. They don't mean anything other than a category. An ordinal level of measurement, on the other hand, involves data that can be arranged in some order. Notice you see the similarity in the words here. Ordinal, order. Let the vocabulary kind of guide you to the understanding. So this involves data that can be arranged in some order, but the differences between the data values either cannot be determined or are meaningless. For example, grades in a school. If you go to an elementary school, we've got kindergarten, first grade, second grade, third grade, fourth grade. The numbers there make sense in order. You attend third grade after second grade. You attend third grade before fourth grade, right? The order makes sense. But it doesn't make sense to add or subtract or anything the numbers. For example, if you have a fifth grader minus a second grader, do you get a third grader? No, it doesn't make sense. So the grades in the school or the letter grades assigned in a course are examples of ordinal levels of measurement. This is just kind of a step up from nominal. So now we have order. Nominal are names, we just have categories. Ordinal, we have order. There's order, but subtraction doesn't make sense. Interval level then kicks it up another level. This involves data that can be arranged in order, and the difference between two data values is meaningful. However, there is no natural zero starting point where none of the quantity is present. An example would be years. We have year 1000, year 2000, 1776, and 1492. What happened in 1776? Declaration of Independence. I'm proud of you. 1492? Columbus sailed the ocean blue. Okay, just checking. These numbers are ordered, and it does make sense to talk about the difference. For example, Y2K happened how many years ago? Y2K was year 2000. 13 years ago. Because we can subtract 2013 and 2000. And it makes sense to say 13 years ago this happened. So there's order and subtraction makes sense. Temperature is another thing where this makes sense, where there's just an interval level of measurement. I can say if it's supposed to be 100 degrees today, and the low today was like 75. So we can say that there's been a 25-degree temperature difference, right? But does it make sense to say, well, 100 degrees is twice as hot as 50 degrees? How do you measure that? That doesn't make sense. And the reason it doesn't make sense is because there is no natural zero starting point. So that's an interval level of measurement where the difference makes sense, but there's no natural zero. Question? Okay, we're not talking about Kelvin because there is a natural zero there, and it does violate. It's actually a ratio level of measurement there. We're not going to convert to the Kelvin scale. I'm glad you mentioned that. Our scientists in the room. All right, now ratio level of measurement, which is what the Kelvin temperature scale is, by the way, is the same as the interval level with the added property that there is a natural zero starting point, where zero indicates that none of the quantity is present. So for values at this level, differences and ratios are meaning. Do y'all know what ratio means? A fraction or a multiple of something. So for example, if I have $50 and you give me $50, I can say I have twice as much money as I started with. And there is possible to have $0. And we're not going to talk about negative dollars because we're responsible people. We don't have negative dollars. So for example, prices of college textbooks where 0 represents no cost. A $100 book costs twice as much as a $50 book. So money's a situation where there could be absolutely nothing present. You could have none of the dollars. And so we have a ratio level of measurement. So in summary, your 4 levels of measurement that we're going to be looking at for data in here are nominal, that are categories only. Think name. Nominal sounds like name, right? It's name only. Ordinal means that we have order. Interval means that we can subtract. And ratio means that differences and there is the differences and a natural zero starting point allows multiples and ratios to make sense. So the 2 types of data that we originally started with, do you remember what those were? Quantitative and categorical or qualitative. Quantitative data can be further broken down into discrete or continuous. And if we have quantitative data, then that can be further classified into either nominal, ordinal, interval, or ratio. So we're getting a lot of vocabulary and terminology in these first few sections. There's not a whole lot of math right now, but we've got to learn to speak the language first. And a lot of the homework in the beginning is going to be reading and vocabulary understanding. So just be prepared for that.